Good morning, good morning, good morning, class. Welcome to your very first calculus lesson. So we're going to get right into it today. I'm going to kind of go over what this video is going to contain, and then we will come together and talk about the questions that you have, so tricky ideas and problems, and clear up any misconceptions. But our goals today is we're going to talk first, what is a limit? So calculus in itself is broken up into three topics: limits, derivatives, and integrals. And we're going to introduce that first of three topics today. So we'll define what is a limit. We'll talk about how do we write limits, how do we determine if a limit exists, and at this moment you can kind of channel your inner Mean Girls if you've seen that movie. And then we're going to end today with just kind of talking about how do we calculate and interpret limits algebraically, graphically, and numerically. I can spell graphically right. I did not. So we'll go through and we'll kind of talk about each one of these. Feel free to pause if you need to pause. That's the glory of the video. There, I spelled it right. But we're going to go through and kind of start with where does the idea of a limit come from? And we're going to actually begin with an application that you did in Math 3, if you took Math 3 at Jones in the small world unit. So here's a basic example of something we might eventually need a limit for. Maybe not this, but we'll work our way to it. So the example says a ball slides down a ramp with a function s equals t squared feet in t seconds. What is the average speed for the first 3 seconds? Okay, so if I want the average speed, we're going to think to ourselves, how do we get the average rate of change or the average speed for this function? Well, I would need to know, where did the ball start at time 0 and where did the ball end at time 3? And from there, I should be able to calculate the rate of change or the speed. So if I plug in 0 into my function, I can see my initial position is 0 feet, which makes sense situationally. The ball is going to start where it starts. 3 seconds later, I can see that the ball is now at 9 feet. So it traveled 9 feet during those 3 seconds. So to find the average speed, I'm just going to take the change in the travel, the distance traveled, or what we call displacement in our physics world, over our time that elapsed, and that would give me 3 feet per second. Okay, now you're probably like, okay, that makes sense. I've done that before, but where does the idea of a limit come? Well, in small world, we looked at the question, what is the speed at 3 seconds? So in other words, what is the rate of change at 3 seconds? So I'm going to write rate of change at t equals 3 seconds. Now I'm going to show you what's wrong with this idea. That's basically saying, like, from 3 to 3, how fast was the ball moving? So now if I were to figure out the slope or the average rate of change from 3 to 3, it would be the change in the position, which the position didn't change, over the time change, which is none. And we end up with this fraction that looks like 0 over 0. Now here is the problem with that. We call this a mathematical paradox. It's actually called an indeterminate. You're like, but isn't that does not exist? Well, here's my argument to you. 0 divided by anything should be considered 0. Like 0 divided by 7 is 0. That makes sense. Anything divided by 0 is undefined. You can't divide by 0. But then, if you think about it, anything divided by itself should equal 1. Like 2 divided by 2 is 1. So why wouldn't 0 divided by 0 be 1? Well, that's just it. We can't decide what it's going to be, so we call this an indeterminate. So finding the speed at 3 seconds is literally impossible for us. So in small world, what you did was learn how to approximate what we call the instantaneous rate of change, or the instantaneous speed in this case. And you did this, I think I spelled that wrong, instantaneous speed. You're going to find throughout the year that I am, a pretty decent, most of the time, math teacher, but I am a terrible speller. So So the number one rule in my classroom, and we're going to hold this rule whether we're virtual or in person, is going to be the fact that this is a judgment-free zone. I'm not going to judge your mathematical questions or mistakes. We're not going to judge each other's mathematical questions or mistakes. And you're not going to judge my bad spelling and typos all the time. Cool? Deal. All right, moving on. So to find the instantaneous speed here, what I would do is I would take a time 3, and maybe I would take a time like 3.001. Or I could go like 2.999 to 3, or 2.999 to 3.001. And what I would do is I would find my position at 3, which I've done. I would find my position 1,000th of a second later, which that's going to be, get my handy dandy calculator out. .006, and then I'm going to find the rate of change between those two positions over the time elapsed, which I can see here would give me 0.006 divided by 0.001, which is about 6 feet per second. Now, this isn't the exact speed. What we've done is we've approximated the rate of change at 3 seconds. So we can probably say within a fairly certain confidence level that the speed at 3 is 6 feet per second. But we didn't find it exactly. We actually just approximated it. So the question is, how do we calculate this exactly? So here's what we're going to do. We're going to go on a little theoretical journey here. So my theoretical journey is I'm going to say, okay, 0.001 second isn't small enough for me to really get the speed at 3 seconds. Like I found the speed between 3 and 3.001, but I could get closer to 3. I would just need a smaller decimal. That's the difference between my two times. So in the first example, we did like 1,000th of a second, 0.001. But what I'm saying is I want an even smaller decimal that's basically 0. So I'm going to actually define that decimal as h. Okay. So what we're going to do is we're going to find the time from 3 to 3 plus that decimal. You could do 3 minus, like if you want to do 2.99999 and 3, like that's also valid. But for me, the algebra is a little easier if I go 3 to 3 plus h. And again, in this case, h is a really, really, really small decimal. Basically nothing. Not exactly nothing, but basically nothing. So if I find my position at 3, and I find my position at 3 plus h, which I would have to plug 3 plus h into the function given, which I could just distribute that out. Square, double, square. It's my little trick for squaring binomials. Now, what I would do is I'd find the speed between those. So I'm going to do the speed at 3 plus h. Notice that this is an algebraic expression, not a numerical expression because I had that little h in there. Minus the position at 3 over the time 3 plus h minus the time of 3. Now, some of you are like, wait a second. This feels familiar to something we did in Math 4. And I'm going to not give you any spoilers, but yes, it is something you did over and over and over again in Math 4. Okay, so if I want to simplify this expression, I would end up with 6h plus h squared over h, because the 3's would cancel. I could factor out an h. Those h's would then cancel, and I end up with an expression 6 plus h. So I can say the way we defined it is that the speed at 3, or between 3 and 3 plus h, is 6 plus h. Now, what is h? Well, h is a really, really small number. but what do I want it to become? Well, the idea is that I want to keep making h become smaller and smaller and smaller until it's basically nothing. And so what we do is this is called limiting the value of something, and the idea of a limit. And so a limit is the idea that we are going to approach, we're going to have a variable or a variable approach a given value that we want, and we want to figure out what would the value of the function or our expression be at that moment. So here, we know h couldn't be 0 in reality, because then we would find that speed between 3 and 3, and that gave us that 0 over 0 or indeterminate. But what I can do with this expression, if this represents the speed between 3 and 3 plus h, what I'm going to do is I'm going to limit or make that h value approach 0. So how I would write that is I'm now going to say I'm going to limit, which I'm just going to use the first 3 letters. It's a common math shortcut. The value of h to approach 0. So this is a command that says I'm going to take something and I'm going to limit its value to be a given number. So I'm limiting the value of h to become 0. Now, the expression that I'm limiting is 6 plus h. So this, you've kind of seen before. This is limit. We've seen limits in Math 4, but not really that much. So we're going to kind of really get into what it means. So we're saying I'm limiting the value of h to approach 0 for this 6 plus h expression. Now, if that's the case, if h approaches 0, I end up with 6 plus 0, which would just be 6. So now I can say without a shadow of a doubt that the speed at 3 is 6, because the speed between 3 and 3 plus h is 6 plus h. And when I limit that h to become 0, then my speed becomes 6. So that, in essence, is the idea of our limit. So a limit, let's go ahead and define what a limit is. The limit, and we'll just call it L, of a function is the intended I spelled it wrong. Intended, there we go. Intended value or height of that function as we approach a given x value. So the limit, we call it like L of a function, is the intended value or height of that function as we approach a given x value. So if you're looking graphically, it's like the intended y. Now, the limit, the idea behind the limit is all about the intention of that value or the intention of that height. Not what the actual value of the function is or the actual height, but what does it do as we get close to that x value? What value does it look like it's approaching? So here's like the example that I give a lot when I'm talking about limits. Let's say we agree to meet at Panera to do some work before school. So I'm going to come from my house, you're going to come from your house. Panera is our limit because that is our intended goal or meeting place. No matter where we're coming from, that is the intended value that we're reaching, is Panera. Now, if we get there and Panera has burned to the ground, that doesn't affect the limit or what our goal was. So Panera can burn to the ground and we would still call Panera the limit of our journey because it's where we intended to go. And when we got there, we were sadly surprised, but it doesn't make a difference because the limit is all about the attention. Now, when we write it, you have to understand that limiting a function is commanding it to do something. And in mathematics, A command always has to have an object. Like the square root is a command. It always has something inside of the radical. Like you can't just write a square root like that and call it something meaningful. Okay, it has to have a number like 4 inside of it to make it matter. Kind of like sine. Sine is a command in mathematics that says find the ratio of opposite over hypotenuse for a given angle, but we have to give the angle, okay, in order for it to work. Log is another example of a command in mathematics. Log base 2, for instance, says find the exponent you would have to raise to get a certain value. So we have to write what that value is. It has to have an object. So when we write a limit, we're going to write the command lim, and underneath it, we're going to talk about where the x value is approaching. So we'll say x approaches c. Now, after that limit has to come your function or the expression of your function. So this is the object. That's like the thing inside of the radical. It's like the angle for sine. It's the object of your command. So without writing the f of x part, the limit part means nothing mathematically. So this command says I'm finding the intended height of f of x as x approaches c. And then the answer to that command is the intended height. So we would say the limit, when I read it, the limit as x approaches c of f of x is L. Okay. Now, this is what we call the general limit, but there is also what we call a one-sided limit. So when we talk about graphically, which is what we're about to get into in a second, how do we find and notate these graphically, algebraically, and numerically? You can approach a given x value from two different directions. And we kind of did this in Math 4, but directional limits are just what we call one-sided limits. So if x was approaching 2, for instance, on a graph, I could go towards 2 from the left of 2, and I can go towards 2 from the right of 2. So because we're talking about a x value, we can come from either side. So how we would notate that is just by putting, and you might remember this from last year, if I want to approach, oh my gosh, my computer is really laggy right now filming this, just an FYI, so that I have to write real slow now. Okay, there we go. Now notice that I'm just writing the command. What I've written, guys, means nothing mathematically. I have to take this and have an object after it. So the object, again, is always the function's name or the expression. Like if the function was 2x plus 3, I could put 2x plus 3. I put it in parentheses, but a lot of people don't. It really doesn't matter. It just helps me figure out what the limit is. Now, if I wanted to, like, communicate that I'm only approaching the c x value from the left, after the c, I'm going to put a little negative sign as a superscript. And if I wanted to say from the right, I would put a little plus sign. So this means from the left. And I'm going to go that it's not going towards the left, it's coming from the left. And this means we're coming from the right. And again, I apologize for my handwriting. My Surface just doesn't have the capability a lot of times to actually, keep up with me. So there's that. Okay, so now what we're going to do is we're going to practice some limits. So here's an example of approaching a limit. Now, I do need to mention that when we talk about limits, if I don't indicate a direction with the C, that means we're just coming from both directions. So if I were to look, for instance, at example 1, at this function x squared minus 1 over x minus 1, this is what it looks like. Now, if I wanted to find the limit as x approaches 1 of f of x, that means I need to go towards this x value. So, and I'm going to come from both ways. So if I come from the left and travel along the function, or if I come from the right, it looks like as I get close to 1 that the value of the function is about 2. Now, if I look at what happens here, there's a hole at 2. That's like Panera burning down to the ground. So even though there's a hole there, if I were to just travel along, it looks like I'd be heading towards a height of 2. So I'm going to say that the limit as x approaches 1 of that function is 2. Now, f of 1 doesn't exist. I'm just going to put DNE for does not exist. Remember, the actual point is not the same thing necessarily as the limit. The limit is as I'm getting close, what height does it look like I'm approaching? So if we look at this second example here, the limit as x approaches 1 of g of x, if I come and follow the function, or if I come from the other direction and follow the function, the limit of g of x as x approaches 1 is a height of 2. Now, g of 1, the actual value of that function, is what the closed circle is, which is 1. The limit does not care where the actual value is. It's just as we're approaching. Now, if we look at this third case, and I want to find the limit as x approaches 1 of h of x, as I go towards 1, either direction from the function, it looks like we're approaching a height of 2. Now in this case, if I look at h of 1, the actual value is 2, so they're the same thing. The point and the limit are the same. Like, congratulations, that's awesome. That's what's going to happen 90% of the time. Okay, but the actual limit part does not care that there's a point there. The point is inconsequential to the actual limit. The limit is just where it looks like it should be heading if I didn't have a graph. Okay. The good news is again, 90% of the time, where the function looks like it's approaching and where it actually goes are the same place. So like 9 times out of 10, we're going to both, actually I'd say 90 times out of 100, we're going to both intend to go to Panera. We're going to get there. Panera's going to be open. We're going to have awesome breakfast sandwiches, do some calculus, and go on with our life. 10 times out of 100, Panera will be burned to the ground, or we get there and they moved Panera and we just didn't know. So we went to a certain address thinking it was there, but they moved it. That would be like case 2, okay? So let's practice some graphical ones. So we're going to look at what happens to y as x approaches 0 from the left, what happens to y when x approaches 0 from the right, and I'm also going to do what f of 0 is, what the actual value is, just because that's good practice. Now, my advice to you, if you're watching this at home, you have these notes available to you. Try these problems. Pause the video right now. Try this example 2, 3, 4, 5 on your own. Okay, and then when you've done them all, play the video, get my voice back in your head, and check your answers. Okay, so if you haven't done these problems yet, pause right now, do the problems, and then start playing again. Okay, that's what I'm going to tell you to do, and hope that you trust me. Okay, great. Now you've done all the problems. You've unpaused me because you did all the problems first, okay? So we're going to go through and we're going to do these limits together. So the limit as x approaches 0, so here's 0 on the x-axis. If I approach 0 from the left, so I'm going to start from the left of 0. I'm going to find my function and I'm going to travel along it. I can see that it looks like I'm hitting a height of 1. If I come from the right, now notice that when I'm coming from the right, like there's this hole there, I'm just going to ignore it. I'm going to keep going from the right. I'm approaching 0, so that's really what I'm focused on. And I can see that that limit is 3. And I can see f of 0 would be 3. Oh, I can't even write today. Let's try this again. Okay, so let's look at this next one. Again, you've already done this problem, and if you haven't, pause me and do it. So here, we're going towards -1, which I've indicated on the graph, from the left. So if I travel from the left, it looks like I'm heading up into space. So I'm going to say that that limit is infinity because there's a vertical asymptote there. As I approach from the right, it looks like I'm hitting a certain value of a height of 2. Now, if I look at what g of -1 is, that doesn't exist. There is no point at 2. Okay, but again, the limit is all about our intended height, not the actual height. Okay, we'll go one more. So here, I'm coming from the left. I'm hitting a height of 2. If I approach A from the right, I'm hitting a height of 2. Now, if I think about what h of A is, h of A is the actual value, that's 3. But again, the limit doesn't care about this like closed circle up here. It just cares about the road. Think about following the road if the function is the road and where the road takes you. Okay. Now, based off these 3 graphs, we want to talk about which of the following limits do exist. So in each of these, I had you find a one-sided limit. What we wanted to do is determine which of these has a general or two-sided limit. So if we go back to the first one, I don't know, guys. Let's look at this. The left limit is 1. The right limit is 3. Now, the actual point is 3, so I could say that the point is 3, but I bet someone in here is thinking that the limit is 1 because coming from the left is the way we read a graph, and because there's a mathematical debate here, we're going to go ahead and say that that limit doesn't exist. Okay, if I look at the g of x graph, okay, coming from the right I hit 2, coming from the left I hit infinity. I'm going to say this one doesn't exist because infinity is not even like a real place, and they're not kind of heading in the same direction. Now, if we look at this last one, coming from the left is 2, coming from the right is 2. And even though there is a debate what the actual value is, the intention, no matter which direction I come from, is 2. So we will say that this limit exists. In fact, that limit is 2 in general. So again, when there's no plus or minus sign, that means we're coming from both directions at the same time. So we can conclude then the following. A limit exists if and only if, Now in mathematics, guys, a lot of times we write that if and only if sentence as IFF. So this is like your little like college mathematical notation lesson. We're going to say a limit exists if and only if the limit as x approaches c from the left of f of x is the same as the limit as x approaches c from the right. So far in this class, we've talked about what is a limit, which is, again, the intended height of a function. We've talked about how to write limits, how they're commands with objects after them. The answer to the limit is the intended height or y value of a function. We've talked about when a limit exists and the one-sided limit, and we've kind of discussed how to find limits graphically. What we're going to focus the rest of this lesson on is just going to be how do we find limits without a graph? So how do we find limits algebraically, and how do we find limits numerically? And then we're also going to talk again a little bit about that indeterminate, that 0 over 0 case, which isn't the same thing as saying a limit doesn't exist. It just says we don't have enough information to determine if a limit exists or not. Okay. So we're going to get into algebraically. I need to take a little swig of water because it's a lot of talking. And we'll go from there. So here's the greatest news of all time. Remember how I said 90% of the time the actual height of the function and the intended height of a function are going to be the same exact place? You're going to assume that happens for every single expression. So for example, number 1 says find the limit as x approaches c of the function 3x squared plus 2x minus 9. Notice that I have the expression in there instead of a name for a function, but either way. So this is saying as I get close to the x value c, what is the intended height of this parabola, which we should know that this is a parabola facing up because it has a positive x squared coefficient. Okay, here's the good news. If I want to figure out what the intended height at c is, I just need to figure out what the actual height at c is. And so all I need to do is plug c into the expression. So the answer to this limit, I'm going to put an equal sign because I'm actually going to find the actual height, is I'm just going to plug in c to this function, and whatever I get out is going to be my limit. So to find limits algebraically, all you're going to do is substitute sub there we go, x into expression. Okay, now notice that this represents the actual value at C, which is going to be the intended value. When I plug in C into that expression, I'm just substituting it in. I'm not writing the limit command because this is the actual height of the function, and what I've done is I found the intention. So I've done the command, and I no longer need to write the limit part in front of this. Okay, so it's just going to be an expression. The limit notation, this piece, isn't part of your answer. Okay, it's part of the command to get you going. It's kind of like saying if I put this, oh my gosh, I can't write, the square root of 25, and I find the square root of 25, I don't say it's the square root of 5. I just say it's 5, right? The square root is the command, and once you've done the command, you don't have to write it anymore. So let's do the second example. Again, here's what I'm going to say. Try it. Pause me real fast. Try this, and then I'll go through it. Unpause me. Okay, you pause me? Okay, great. Now, I'm unpaused, so all I'm going to do here is I'm going to plug in 5. I'm going to substitute that value in for x and find the actual point at 5 because 90% of the time, it's going to be the same thing. So if I work this out, 5 squared is 25 times 4 is 100. Make sure you square before you multiply. Minus 25 plus 6. That's 75 plus 6, which is 81. So I get a actual height of 81, which would be the intended height as well. Okay, moving on. We're going to try some other ones. And again, pause me, try them. If you wanted to like pause me, try one, unpause me, do that. Work this how you can under the given situations of how we're dealing with life. Okay. But try them before you let me do them. That's the only thing that I ask of you right now, other than the number 1 rule, which is judgment-free zone. Okay, great. Here we go. So I'm going to plug in 2 and get that limit, which is 9. This one, I'm going to plug in pi over 6. Ooh, here we go. Cosine of pi over 6 over sine of 3 times pi over 6. Okay, so now we're going to evaluate this. If you're like me, I always have to do my reference triangle here. So pi over 6, I know pi over 6 is 30. So my ratios would be 1 to root 3 because it's a 30, 60, 90. So cosine would be square root of 3 over 2. Now the sine of 3 pi over 6 is the same thing as sine of pi over 2, which is 90 degrees. That's at the top of our unit circle. It's a quadrantal angle. So the point there is 0, 1. Sine is just going to be 1. So I end up just getting square root of 3 over 2. Okay. So a little bit of trig review built in. You got some good practice on your summer pocket, but it never hurts to keep practicing. Okay, number 5, we'll try this one. So I'm going to plug in 2 first. So I get 2 squared plus, that's a square, 3 times 2 minus 10 over 2 squared minus 2 minus 2. So that's going to give me 10 minus 10 over 4 minus 4. Okay, now look at this, guys. I end up getting 0 over 0. That does not exist. Okay, if it was like 7 over 0, then I would say the limit doesn't exist because it's not a real number. If it was 0 over 7, I would just say it's 0. But since it's 0 over 0, that's an indeterminate, okay? So not dne, it's an indeterminate. So what we need to do is we need to manipulate or think about what can we do to our expression here to maybe simplify it or rewrite it. So when this happens, in next lesson, we'll talk a little bit more about how to deal with indeterminates. Let's think about how we can rewrite the expression. So you're probably thinking to yourself, oh, I don't know. When in doubt, I'm just always going to factor. So here's what I'm going to do. I'm going to rewrite the expression. Now, because I'm rewriting the expression, I'm going to make sure that I rewrite my limit notation if my Surface would actually like catch up to my voice. There we go. And what I'm going to do is I'm going to rewrite the function. Now, I'm going to keep that command in there every single time I rewrite it. So I'm going to go ahead and factor this guy into x plus 5 and x minus 2. And my denominator, I can factor that into x plus 1 and x minus 2. Okay. Now, if I write it in factored form, I can see here that I can simplify this expression. So if I simplify this expression, now I have a new problem to do. The limit as x approaches 2 of x plus 5 over x plus 1. Okay. So again, I rewrote that limit command because I haven't plugged 2 into anything. I'm just rewriting these expressions. And every time I rewrite an expression, I need to put the command down so that I know that I still have to do the command. So now I can't simplify this expression anymore. What I'm going to do is erase this so it actually looks like a number and rewrite 2. There we go. I'm going to plug 2 in. Now at this step, guys, we are actually evaluating and finding the height at 2. So I'm going to write it without the limit command because by plugging in 2, I'm actually doing the command. And when I do that, I end up with 7 over 3. So does this function have a limit? Yes, the limit is 7/3. Does it have an actual point? No. So what I would say to you is thinking about this graphically, you need to think back to like your math for rational functions. When we have a 0 over 0 case, a lot of times what that's going to do is create a hole in the graph like we saw on the original graph. So like if I had a hole in a function, the limit would still exist. Panera has just burned down to the ground. So this is a case where Panera has burned, but it's still on the corner of State and Congress. So that 7/3 is like its address. It's the intended value of the function. There is no actual value here, but there is an intended value. So there's a hole or a height that the function is approaching at that moment. All right, last thing, and then we'll be done. We've done a lot for our very first lesson. So kudos to you for following along with my long-winded rambles, okay? Now, numerical. That's going to be anytime we use like a table. Okay. Technically, it is never possible to find the exact limit from a graph or table because we can't zoom in close enough unless we know something about what creates that function or table. Like if we had, for instance, an expression or a function, then that we could then figure out what the limit is based off the graph or the table. But if we don't, then we're just kind of technically approximating. Nevertheless, we're going to assume that like we can find the limit from these tables. So for each of these functions, f, g, h, j, and k, if you notice here, I've created a table that starts at 9.997 and then goes through 10.003. So what we're going to do is we're going to estimate what the limit as x approaches 10 is of each of these functions, okay? So maybe try f of x, pause me, try it, unpause me. If you want to follow along with f of x, then definitely pause me to try g, h, j, and k before unpausing me to figure out the answer, okay? So again, think through these problems before I do. It's going to help tremendously in your understanding. So if I were finding the limit as x approaches 10, here is my advice to you, okay? I don't actually care about the value at 10. So I'm actually going to cross all the points at 10 off because remember, the limit is about approaching 10. It's not about what happens at 10. So if I come from the left and approach 10 on f of x, if I look at the pattern of numbers, it goes 1, 3, 5. So if I were to continue that pattern in my mind, it would go 1, 3, 5, 7. Okay. So coming from the left, my intended height of f of x would be 7. Now, if I'm coming from the right, that means I'm going towards 10, starting at 10.03. I have 5, 7, 9, 11. Because they are not approaching the same number, from the left I'm heading towards 7, from the right I'm heading towards 11, we would say that this limit does not exist. So now if I look at g of x, again, pause me, try G, H, J, K, unpause me, or, pause me at each one, whatever you want to do. Okay, but pause me is what I'm saying. You got to pause me. Okay, so g of x, I go negative 4.01, negative 4, negative 4. If I look at it, it just kind of looks like it's slowed down graphically, and it's just heading to a height of negative 4 from the left. And then from the right, negative 3.99, negative 4, negative 4, it looks like it's also hitting negative 4. So I'm going to assume that limit is negative 4. I actually can't be 100% certain because I can't zoom in close enough. 1,000th is not close enough, guys. So let's see here. 6666. Ooh, that's a little bit like the devil. Okay, 666. I'm going to assume it would go to 6. 777, I'm going to assume coming from the right at 7. That means there's some sort of jump in the graph here. I'm going to say this limit does not exist. Now the actual graph's value is 6, but remember, we don't care about what the actual point is. We care about what happens as I get close to that point, not what happens at that point. Okay, so let's look here. 0.50, 0.52, 0.54, that should be 0.56 coming from the left. If I head from the right, 0.62, 0.60, 0.58, 0.56. I'm going to say 4.56 is my limit. 60, 61, 62, 66, 65, 64, 63. I'm going to say 5.63 is the limit there. Okay. So you'll have a couple of these graph ones to kind of look at, a couple algebra ones to try for homework, a couple graphical ones to try for homework, and a couple problems where you have to do the average speed and the instantaneous speed. I will see you guys in class, and that's all I have for you. So have a